In this video, we'll take a look at talking through the assumption checks, how we sort of generate the graphs to go through them, and what exactly these assumption checks are in order to actually do a simple linear regression and do it appropriately on the right sort of data. So we'll take a look at going through that. I'll use an example located in our group data set called the World Cup 2014 forward goal totals. And specifically, we're going to look at going through and seeing if appearance can describe the number of goals scored. So how many times you appeared in a game, does that affect the number of goals you're going to score when you're a forward in soccer? I have a slide in here sort of just kind of explain and show sort of everything I'm going to be selecting in StatCrunch in a second. Where we have our X variable and our Y variable, our explanatory and response, respectively. It's things you've seen before. But we're going to start checking off some of these graph options as well as some things to save. We won't necessarily talk about some of these things, but they might be helpful in actually recognizing these are some of the ways you can predict some values as well as look at individual residuals. Okay, so let me go ahead and switch over to StatCrunch. Okay. So here's the data set in question. So we got a bunch of different players, ages and heights. We're interested in these two columns, it's appearances and international goals. I'll even expand that out a little bit. And we want to do a simple linear regression to see if appearances has an effect on the number of international goals scored. Okay, so we took a look at last week where we looked at regression within our stat option, and we looked at simple linear so far. And I'm going to plug in my explanatory variable, my appearances, and I'll plug in my response variable, international goals. Now we've took a look at in some of the other videos that here are our hypotheses, and we can do some confidence intervals on the slope, do some prediction intervals and confidence intervals for certain predictions. But we want to make sure that when we're doing these things, that simple linear regression is actually the appropriate thing to actually do. In order to determine if it's appropriate, we need to check the assumptions for it. So in order to check the assumptions, we need to start selecting some of these additional graphs. Okay? The graphs are going to be this fitted line plot, the histogram of the residuals, the QQ plot of the residuals, as well as this residuals versus X values. Okay, since I don't have a keyboard, you need to control click or command click depending on if you're a PC or Mac respectively. Or you can just sort of click and drag all of these up here. There's a couple of them in here we don't really care about. This residual index plot, I'll show that in a second, don't really care about. And if we want to save our residuals, the ones we're actually looking at, as well as our studentized residuals and predicted values, we can do that as well. Not necessarily necessary for simple linear regression, since all these graphs are going to be generated for us within the StatCrunch output window. But you can go ahead and select these if you want. Same sort of deal. Control click or command click each one. And click compute. And you'll see that they're saved in here, so you can see exactly certain individuals, what sort of predicted value they have, what's the residual, the difference between the observed and predicted, as well as the studentized residual, sort of standardizing like a z-score. And you can look at specific players. I'll pick out Luis Suarez as one. Okay, but now we got some windows in here that we're interested in, and you'll see that this is our regression output, things we've seen before. This is our scatter plot. I had some extra options selected in here to sort of do and show those confidence intervals and prediction intervals that we calculate. And you can see this listed up here. Not necessarily to do. Residual index plot, we don't care about that graph, so you can completely ignore it. Histogram of the residuals, we'll talk about what that is. QQ plot of the residuals. And then the residuals versus appearances. So we're going to go through each of these different graphs because they're going to be very important for sort of what we're going to be looking for. So I'm going to go back to my PowerPoint. And I want to present. Okay, so we have our output here. And just to kind of re-mention, hey, is our model useful? Does appearances describe international goals? Taking a look at that p-value, yes, we are describing it, but it might not be appropriate to say that conclusion if our assumptions are not met. So what are the assumptions we need to take a look at when going through simple linear regression? Luckily, when we do simple linear regression, when we fit a line to some data, our actual assumptions are LINE, linearity of the data, independence of the observations, normality of the residuals, as well as equal or constant variance, where the LINE is going to come into play. So we're going to need to check with each of these things with our data set. Okay. Again, reminder of what the residual is. It's just our observed minus predicted. And we're going to be using these residuals when we're talking about sort of the model we fit. So we're going to be looking at these different graphs and the ones we just sort of made. Okay. In addition to that sort of scatter plot we traditionally looked at last week. So there's a histogram of the residuals in the red. So we're going to be using this graph to take a look at the normality of the residuals. We want to sort of see a bell-shaped curve, and you can kind of see what the bell-shaped curve would look like in the red in this graph. So that's one thing we're going to take a look at with that graph. That's really the only assumption with that one we're interested in. We can also check normality with the QQ plot. And we'll talk a little bit about what we're looking for in there. But essentially we want to see nothing. We want to see those dots along that red line. And then the residuals versus x values are a couple of things we can actually see in here. We can actually see linearity, just like the scatter plot or the fitted line plot. We can see if there's a curve within our data, which is not something we want to see. We also can check for equal variance or constant variance. Sort of what does that mean? What is this fanning megaphone shape we're wanting to avoid? We're going to look at that specifically coming up. So let's go through and check each of these for our data. Okay, so we're going to check linearity. So are we fitting a line to data that's roughly linear or linear in nature? What we don't want to see is this really bad example down here, where clearly, if we fit a line, it's not doing a good job. So we want to fit a line like we are here to something that's obviously not curvature. There's obviously no curvature in there. Okay. It doesn't appear to be any real curvature within this. Maybe if you really squinted hard enough. We're okay on this one. When you'll take a look at assumption checks with regression, we're using a lot of graphs. We're not necessarily using numbers per se. So there's a little bit more wiggle room when you're taking a look at some of these graphs, which is why you'll a lot of times hear someone say an obvious curve. If there's an obvious curve, then we definitely want to stop. But I don't really see an obvious curve popping out in this data set. Okay, so linearity, no question in it. Okay, or some questions if you really want to see something like this in there. Really, it depends on how hard you're going to be looking at. But again, we'll also mention that when one assumption fails, you tend to see more assumptions fail as well. Independence, this one has no graphs, and for the sake of our class, this is something that's going to be sort of assumed. We don't want you to say that when you're checking the assumption. We still want you to kind of think about it, because in the real world, you might not see data that's actually going to be independent from one another. So what do we mean by independence in this case? Well, we're actually meaning independence between the observations. Okay, so in this case, we're looking at players. We don't want one player's goal total to affect another player's goal total. Okay, we're actually looking for dependence between the two variables. This is actually more between the observational units, between the actual players in this case, or between the different rows in the data set. So we want each row in the data to be independent of the others. Okay. Again, for our data sets we're taking a look at in this class, this is going to be the case, but you want to recognize that that's what's going on with the independence. So you might run into the issue with some other data sets outside this course. Normality of the residuals. So we want to make sure that the residuals, if we plotted them as a histogram, that they look somewhat normally distributed. And one way to check that is the histogram. The other one is the QQ plot. What we want to see in the QQ plot is these dots sort of fitting this line. As you can see, I'm sort of dotting up. We want to see that exactly that line. You're not going to see exactly always, but you kind of want to see a rough pattern along that line. we don't really want to see anything like this really bad example, which is somewhat what our QQ plot's looking at. So it's not looking too great there. Okay, we want to see those points roughly along that line. Okay, and that's what we're checking with normality. One thing to note too is when you check the normality and check the other assumptions, when we're using these graphs, we're actually referencing these graphs in our assumption checks. You want to specifically say, which sort of graph am I getting this assumption from? You want to be very specific. Assumption violations for the equal or constant variance. This is a really, really bad one. Because we want essentially an equal spread as we go from the left-hand side of this graph to the right-hand side. What we don't want to see is some sort of megaphone shape. Another good way to say it is you don't want a sideways tornado. So a tornado sort of tipped on its side. Where you can see here clearly as we go, right here there's not too much of a spread, but as we go down here, pretty big spread in our data. We don't want to see that. This is a very clear example of this assumption being violated. What we want to see is something more like this, where you just see a random scattering of dots, roughly the same distance above and below this zero value as you go left to right. Essentially what you kind of want to see with a lot of these assumption graphs is something very boring. You don't want to see really anything in it. When you take a look at this graph right here, you just see a bunch of dots in like a box shape. Nothing too sort of stand out with that. But if we go to our sort of actual example with our soccer data, we can see that, wow, it's really spreading out as we go from left to right. Not what we want to see. QQ plot. There's a little curve in there. Something we don't want to see. Okay, so how do we sort of summarize a lot of these different assumption violations? We kind of took a look at it before, but these are the sort of graphs you want to reference. Your scatter plot, which will look at linearity. I'm going to say it's okay. We got bigger issues to kind of deal with a little bit later on, but linearity seems to be okay based upon that scatter plot. One player doesn't affect another player in terms of goals scored or appearances necessarily. So they're independent. Normality. Okay, so we take a look at the QQ plot. Okay. And then the big one, the equal variance. And we'll say clear non-constant variance. Essentially, the variance is changing with the sort of data as you go left to right. We'll be even more specific. It increases with more appearances. And this is based on the residuals versus predictor. Or X, or you can actually throw in residuals versus appearances. They all essentially mean the same thing. Okay. So we had assumption violation we all can agree on with the non-constant variance. So when that means we have assumptions that are not met, okay, we don't actually have results from this method. We don't have results from simple linear regression. It's not appropriate to conclude that there is a linear relationship. There's assumptions that need to be met in order to actually conclude that, and clearly we don't have those. We need some sort of more complicated method, or if you take, say, STA 363, you'll find ways to sort of alleviate some of those assumption issues, where you can maybe do some transformations. Instead of looking at the response, let's look at, say, the log response, or the square root of the response. And it'll change some things how we go about this. And sort of what you want to do to actually do the transformation is also another tool outside the scope of this course. But do recognize that if you don't have assumptions met, it's not appropriate to claim the particular results in that test or in that sort of procedure. So you want to be very careful and cognizant of that. Okay, I got a couple other slides I will include within this, going over some reminders from the past week and stuff, how to interpret some things. But hopefully this video was helpful in terms of just talking about these assumptions, how to go about them, how to read them, and what sort of graphs you're looking for within each of these. So hopefully that was helpful when you go about doing the regression lab as well as preparing for the final exam. Okay, have a good one.